is Gergely Daroczi from the SpareCourse team, and we'll try to focus on the fact that we spin up a couple thousand servers to see how those behave under load when it comes to LLM Inference for prompt processing and text generation. So that's what I try to cover today. Before we dive into the details, I wanted to build some credibility for the project so that we are not affiliated with any vendor and trying to bias things. So SpareCourse has been funded by NGI Search last year, which is an EU consortium. So this guarantees that we are vendor independent, fully open source and dedicated, remaining that. We were accepted to the NVIDIA Inception program and also got some cloud credits for the sake of benchmarking. But again, it's not kind of sponsorship or affiliation or something like that. You can totally get the same amount of credits if you start a startup company. We presented at a few conferences last year. I was happy to be at Berlin Buzzwords and Kubernetes Community Days and so on. But again, this is the first PyData. Super excited about that. And besides some offline events, got some traction from online communities. Like last year, the Pragmatic Engineer mentioned us, got a couple thousand likes and even some good threads on Reddit about benchmarking. And I'm dedicated to continue that. So what we do, we curate open source tools, related documentation, including database schemas and so on, so that you can warehouse cloud resources, including vendor metadata, regions, availability zones, servers, related prices, traffic price, storage, and so on. Fortunately, you do not really have to run our open source tools because we have a managed infrastructure so that we run that every few minutes. So we track the spot instance prices very frequently. We also spin up all these machines, run hardware inspection tools on them, run 500 different benchmarking workloads and publish that so that you can use that for your server selection. There are also some API endpoints and SDKs so that you can use that in a programmatic way. And you can also download the database dumps and so on. There are a few other open source tools that we maintain related to open benchmarking, and these help you to track resource usage, both in Python and R, so that you can find the cloud server for your tasks. So this is about SpareCourse, and now actually let's get into the Navigator project, which is doing all the benchmarking and so on. Some high-level details about what we do. We integrated with 5 vendors. We track around 350 availability zones all around the globe, close to 2,500 servers inspected right now. And because we look at around 500 benchmark scores per server, it's around 1 million benchmark scores that we have in our open data set. We update the spot instance prices every few minutes. So over the past 2 years, we collected a couple tens of millions of data records that's available on our homepage. Everything is run in the public, so we use GitHub Actions for everything, even for starting the cloud servers at the hyperscalers, at Hetzner, at UpCloud, and so on. So you can see the raw standard out, standard error of all our jobs in the GitHub Action output, and also the results are recorded in Git repos. So if you do not like our database schemas, you can grab the raw data and do whatever you wish with that. The easiest way to use this data is still going to sparecourse.com, and we have a web application where you can filter these servers, click on those to get some more details, like I just clicked on G2 standard 16 at GCP. You can see some server details here, and I will show that we look up like level 1, 2, 3 cache amounts and a bunch of other details as well. We track the prices over all regions and availability zones, and here comes the benchmarking part. Let me focus a little bit on the memory bandwidth widget on the top left corner. So we look at the performance of read, write, and mixed operations using various block sizes. And you can see that once we increase the block size, the speed decreases. This is because we are using block sizes larger than the cache amounts. For the sake of helping to understand that, we also include the level 1, level 2, level 3 cache amounts of the CPU so that you can see why this is dropping very heavily. And well, you can see like what to expect from the server. More hands-on example is compression algos, compressing the compression using like a dozen different algos, using single-thread, multi-thread approaches, different compression levels, and so on. Looking at OpenSSL block ciphers, hash functions using different block sizes, and you can see the raw performance here. We also run general benchmarking tools like Bestmark. So here you can find some CPU-related metrics, memory scores, and also Geekbench 6 for single-core and multi-core as well, which includes a bunch of different workloads like image processing, NLP, compiling software, and so on. So you can find all that. We also do a lot of CPU burning. This is using StressNG, and actually in the background just dividing integers a lot of times and just measuring the number of hops we can do in a second. And we use that metric so that we can see how well a CPU can scale to an application that can use multiple cores. Here we can see the effect of hyper-threading after hitting 50% of the logical cores or virtual CPUs of this server. You can see that the relative performance drops, and usually that drops to like 50%, which is, I think, super important when you are doing ML model training and so on, which do not really scale well with hyper-threading, and you just want to disable that. We have the LLM Inference speed benchmarks that I will share in more details, and a bunch of other application-specific stuff as well, like looking at the performance, throughput, latency of static web serving or databases. You can also compare servers, like any combination of those 2500s in tables like this one, including the CPU model and so on. You can also generate the previously mentioned charts for multiple servers. For your programmatic needs, there's an API endpoint, well, actually multiple API endpoints, so that you can search and get details or pricing information about the servers in a standard way. Here's a quick Python script so that you can load the SQLite dump that we update every few minutes. Currently, it's like 500 megabytes, so it's getting pretty sizable even without historical data. But once you load that, it's super easy to query, let's say, an AWS machine here. You get the server ID, vendor ID, some description about it, and then the CPU information up to the actual CPU model, which was collected thanks to hardware discovery. Also, we'll look at memory speed, the actual DDR generation, if that's available, and let's say GPU options. So this guy comes with a single T4, but to show you the depth of the data, we even tracked like firmware, BIOS version, and so on, which might be useful when you are using specific drivers and so on. And of course, storage and included traffic, that's all included. You can grab the database if you do not like the APIs or the web application. So the Navigator is a collection of open source tools that you can find on GitHub. Feel free to use that and provide feedback. For now, I will focus on the inspector, which is doing the benchmarking for the sake of this LLM benchmark talk. So we started with a Docker image because all our benchmarks are run through containers so that it's easy to deploy. This is a Docker image which supports ARM and x86 as well. It can run on CPUs and can use CUDA in the background as well. And here comes the compulsory AI image that I wanted to include here. I asked, I think it was ChatGPT, that I wanted to have like a fun image which shows that we support CUDA, and it came up with this. Like, can you see the transparent background? It's crazy, and well, the Barracuda, it's really difficult to describe what's happening here. Anyway, I included it here. More detail about the actual image. So x86 and ARM support included. We bundle Llama CPP or C++ binaries for different CPU families and CUDA builds as well, which been a little bit tricky because we needed to look up in a recursive way all the linked libraries from multiple Docker images so that we have, for CPU build, for the CUDA build, and so on. And anyway, it works, and we run it on more than 2,000 servers with different hardware and managed to get it right. There's also a Python script which is doing the actual benchmarking, which starts with hardware discovery so that we know which version of Llama CPP we can use, does the path overrides and so on so that it can find the linked libraries. Then it starts a background thread downloading the models from Hugging Face, starting with the smallest model and in a sequential way finishing off until it downloads everything. We also try to find the NGL setting, which is a shorthand for the number of layers we can or we want to load into VRAM, so the memory of GPUs. If there's a GPU available, of course you want to hit the sweet point where it's not running over memory, and but you are loading the max number of layers possible so that it will be fast. And then we start all the benchmarks. So regarding the models that we have benchmarked, we included small models like the small LM, which has only 135 million parameters. And we included larger ones like Llama 3.3 with 70 billion parameters. And we try to load all of these on all these servers out there. Of course, you can imagine that on tiny machines, we were not really able to run all these models, but we started with the smallest one and kept trying until things just exploded and we stopped. So regarding the speed of these, we didn't want to burn a lot of money on this benchmark, and by lot I mean more than like $10,000 or euros. So we needed to find some sane thresholds. Let's say we are doing prompt processing for a short token length, so let's go with 16 tokens. The expected TPS that tokens per second that we set was 2, so that we can benchmark small machines as well. But once we have larger text than, let's say, 16,000 tokens, if we go with 2 tokens per second, it could run for hours, and we do not want to waste time. So in those cases, we expected a much higher tokens per speed. Same stuff for text generation, which tends to be a bit slower than prompt processing, so that's why we had a bit lower TPS. Like we were okay having 1 token per second for text generation so that we can load some models on smaller machines as well. And the timeout set for every single benchmarking scenario was taking into account how much time it might take that we load the model into memory. And well, sorry, let me go back to the previous slide because I included the model names here. So we were using the quantile models, which are pretty small. You can see that the smallest is like 100 megabytes. The largest is 42 gigabytes. Loading that into memory takes some time, so that's why we had to include that in our thresholds. We run 5 iterations for all benchmarks, so that's why we multiplied by 5 and had some overhead. Here you can see an actual output, and this is from a GitHub action, so you can go there and find the same stuff, but I have some annotations here. So this is running on a Hetzner machine and using the CPU build of Llama CPP, downloading the smallest model. This is running in a background thread. You can see that it was downloaded in like 300 milliseconds. The model was found, and then we right away switched to downloading the second model so that while we are benchmarking the small LM model, we can continue the download in the back. So NGL is set to 0 because there are no GPUs in this machine. We start the benchmarking with 16 tokens. You can see that the threshold to run this is 41 seconds, but we managed to run it in like 350 milliseconds. This was super fast, so we managed to run it on larger tokens. In the meantime, we managed to download the previous models, so we switched downloading the Llama 7 billion model, and we continued benchmarking the small LM model in the background, and it timed out with 4,000 tokens, so we stopped and switched to benchmarking test generation until we could. We needed to stop after 1,000 tokens because it timed out after like 2 minutes. So we did the same for all the other models until we hit some bumps with the Phi 4 model, which is a 14 billion model. As you can see, we only managed to do the benchmarks for 128 tokens when it comes to prompt processing, and for text generation it failed with even 16 tokens, so we just gave up and didn't even try loading the largest model, the 70 billion one, because it would have timed out anyway. So we stopped the download and killed the server right away to save some cost. Just imagine some servers out there cost $250 per hour, so stopping early is pretty wise in many cases. This is the raw output, JSON lines files. You can find that in the Git repo, and just scrolling down a little bit, you can see all the different benchmarking workload, like 16 tokens, 128, and so on, and the actual measurement. So it was around 500-ish tokens per second for prompt processing with the smallest model. You can find the results on our homepage, which is embedded here in these slides. And if you are interested in the fee model as well, you can see that with this small machine, which costs like a few euro cents per hour, you can even run the 14 billion parameter fee for model with 2 tokens per second. You can spin up many of those and distribute your workload. For text generation, similar widget, although fee4 was not able to be used here. Regarding the number of servers that we managed to run here, this is a curl command hitting our public API, looking for the number of servers where we managed to run the smallest model. It's around 2200-ish. If you're focusing on the largest model, we still managed to run it on close to like 1,300 servers. And if we switch to text generation instead of prompt processing, which is much slower, and also tweaking the number of tokens to a bit higher number, then we still get like 600 different server types where we have a benchmarking score. So to navigate that, and let me actually go to our homepage and show you how you can use that. I'm going to the servers, and hopefully internet speed is all right. So here in the sidebar, you can filter for different things, like you're looking for a specific GPU, you can select that, you want X amount of VRAM and so on, you can do that there. It's by default ordered by the best price, and you can see that there's some bug, like Azure just announced the server which goes for $0, so it's not unknown, but it's actually shared as 0. A bug fix for that is being deployed, so sorry for that. But anyway, all the other servers are ordered by the best price, and there are some other details as well. Like, let's include the actual CPU model, and let's see also the best on-demand price, not only the best spot price as well. So you can see all the CPU models and a few other things here. There's this benchmark column, which by default shows the stress NG scores, which is burning CPU, doing integer divisions. If you click on this guy, then you can select another benchmark category. Here I will go for LLM Inference speed. And again, we have quite a few other options here. So if you are into like compression, hopefully you can find a benchmark score there as well. So clicking here, and we could filter for, we were looking for llama, and let's do prompt processing for 128 tokens. Now I'm selecting the smaller llama model. Where is the text generation? And yeah, okay, let's go with this guy. So now the benchmark column has been updated, and you can see that it's missing for many of the small machines because we were not able to load that into memory. Let's reorder this table by the benchmark score, and you can see that some servers managed to do 161 tokens per second using some powerful GPUs, like there was an A100 here. In some other machines, there were like 4 A100s with a lot of VRAM and so on. So these are the fastest one. Usually you're not looking for the fastest, but maybe for the most cost-efficient one. So let me switch on that column. Ordering. Here we are looking at the token per speed that you can get for $1 per hour amount. So it's like dividing the benchmark score by the best price. So you can see that Still, the GPU option is the best here. We can get up to like 1,500 tokens per second for a single dollar per hour. This is a much less powerful GPU than the 800s, but it costs much less. If you look at the second option, there are no GPUs here, but this is a recent AMD CPU model, which can handle things pretty quickly. So actually using a CPU build to serve this model with 7 billion parameters makes much more sense because it costs like nuts compared to the GPU option. So you can start some of these servers and get away for a fraction of the price when it comes to serving LLMs. Also, let me grab the opportunity to show you how you can compare different options. So I'm marking a few servers here, skipping the G2 standard 8 because that's pretty much like the first option, but with more memory and so on. Clicking on compare, it should quickly generate if the Wi-Fi allows a table for you and all the tiny details. Like you can see that all these guys have 4 or 8 CPUs. Looking at the GPUs, there are 2 without any GPU, and scrolling down you can see all the benchmark results. You can get all the details and check if you are looking for a specific option here. Let's scroll down to the LLM inference speed, and we were looking at Llama 7B. You can see all the benchmarks and decide like which one you would like to use. Again, usually it's the cost efficiency that's the most important thing. All right, let me get back to my slides. These are the backups, and let's continue. So, which is the best server to serve LLMs? As you have guessed, it really depends like what you really want to do with those LLMs. It will depend on the actual model size and also the workload, if it's prompt processing or text generation, the token lengths, and so on. Quick example, here there's an Azure versus AWS machine. One has only 4 vCPUs, the other has 16. Also, it's like 16 gigabytes of RAM versus 128 gigs, so it's a magnitude larger machine. And if you look at the speed for prompt processing and text generation for a small model, it's pretty much the same. So you probably do not want to overpay and just go with the smallest machine. If it comes to prompt processing with a larger model, then you can get like twice more performance on a machine thanks to the modern CPU. So again, look up the actual numbers for your specific workload, and hopefully this database can help you find the best resource. Of course, there are some limitations. First, Llama CPP cannot really scale to multiple GPUs. I mean, if you have a large model, you can load the layers into multiple GPUs, but if it fits in a single GPU's VRAM, then the other GPUs will be just sitting there. You could overcome this by starting multiple instances of Llama CPP, but anyway, the benchmarking would become much more complex and less easy to interpret, so we just take it granted that there's a limitation. Also, we need CUDA for the GPU accelerated inference, so AMD, Habana, and all the other GPUs are not supported, unfortunately, and even some NVIDIA GPUs are incompatible, it seems. If you are interested in more details, check out on the homepage. We have a dedicated page for GPU accelerated instances. So regarding the license, it's 100% open source, but there's always a but. Probably you do not want to run this at home. As I mentioned previously, it can cost a lot of money to run this. If you are interested in the actual numbers, we have burned quite a lot of money when running just this single LLM benchmarking workloads. And things went a bit crazy with Azure. So previously, we managed to terminate things right after stopping the instance, but Azure charges for stopped instances as well. It took some time that we realized, so we burned around 10,000 credits. Fortunately, we didn't have to actually pay for this. Regarding the next steps, and I know I'm running out of time, so we'll speed up. Of course, we would love to onboard new vendors, so we need to integrate them in the ETL tool and in the runner so that there's a standard way to spin up machines and no need to master AWS, GCP, and other CLIs. But probably more exciting is to add new benchmark workloads. So we already support a bunch of different categories, but there are others that we could add. And when I was thinking about benchmarking, I've been working as a data scientist for a long time and been using random forest and GBMs for many, many things, which are still very relevant, I think, nowadays. So I just remembered old friends' slides that GBMs are still, useful today. So let's see if we could do some related benchmarks. Szilárd Pavka, if you have not heard about his benchmarks, been doing pretty interesting things for the past decade or so, and he have run benchmarks for linear models, random forests, GBMs, deep neural nets, and so on. Later, he focused on GBM implementations, looking at XGBoost, LightGBM, XGBoost, and so on. And he has been updating that recently as well for newer hardware. So I thought this could be a good starting point. If you're not familiar with the benchmarks, he's using the airline data set. And for the training data, using 100,000 or 1 million or 10 million records from the years of 2005 and 6. Then using 100,000 records from 2007 as the test data set. And the response variable was if a flight was delayed by more than 15 minutes. Looked at these 4 GBM implementations and the metrics being tracked for the training time, and we're looking for the fastest GBM implementation so that you can quickly iterate on your models. And of course, AUC, that's a pretty important metric as well. And then looked at CPU and GPU options as well. Here you can see some results are running on CPU and GPU. These are pretty old instances, but there are some more recent results, and I'm just about to run this on more than 2,000 servers, so we'll see more about that. The plan is to use the training and test files that Szilárd provided, port the R scripts to Python so that it's easier to deploy. But there are a few related questions like, which GBM implementation should we run? Are we really interested in benchmarking all 4, or it's okay to go with XGBoost and so on? If you're interested in the details, please let me know. I'm really looking forward to get any feedback before spinning up all these machines. I know there's not much time for questions, but I happen to sit right outside of this room, so please say hello if you're around, and I would love to discuss what you would find useful when it comes to benchmarking GBMs. And for the online folks, I also included my contact details. Please let me know what you think and what you would like to see in the next benchmarks. And having said that, I'm stopping hopefully right on time. Thank you very much.
Thank you, Gergely. Is anyone having any questions? Please raise your hand. Otherwise, I'm going to just ask the question raised on the platform. So do you have any plans to integrate spare code results into any popular MLOps or cloud orchestration tools so the users can automatically provision the most cost-efficient instances for their workload?
Yeah, that's a really good question. And actually, we do have support for some of those. Metaflow was the first that we integrated, which means, and well, if you go to the resource tracker part of our homepage, there's a Python package, fully open source, that you can use to track resource usage of your Python scripts and R scripts as well, because there's a related R package. But you can use that very easily from Metaflow, because this is an extension. After installing the resource tracker package, you can import the related track resources decorator right from the Metaflow meta package. And if you add that to any step, then the resource usage would be automatically tracked in the background, which includes CPU, memory, GPU, VRAM, storage, network in, network out, and so on. And it will generate some charts for you so that you can inspect how the CPU usage changed over time. It will provide you usage statistics like peak memory usage, average CPU usage, and so on, so that you can decide what's the best resource. And it also recommends automated resource usage, like you can use one or multiple GPUs and so on, and can also pick the cheapest server to run the related workload. So what's being worked on is to not only do the reporting, but to automate this resources decorator update. That should be ready in a couple of weeks, and more integrations coming up as well. But for now, it's mainly Metaflow.
Thank you so much. I think that's all the time we have. Give it a round of applause.
Thank you so much. Thank you.